Okay, we are back and better than ever. We are talking about expectation. A lot of this is intuitive. Very easy example to talk about expectation. If we roll a die 120 times, basically all they're saying here is how many of those rolls should we expect to be a 6? Well, if it is a fair die, that is that each of the numbers 1 through 6 have an equal chance to come up, how many of the 120 rolls should we expect to be a 6? Well, each of these individual outcomes has a probability of 1/6 to come up, and if there's 120 rolls, 1/6 of them, or 1/6 times 120, or 20, is what we would expect to come out as 6. Will we actually get 6? We might, but we're not sure. But that's we have to have some expectation, especially if the die is fair, and that expectation is 20. So that leads to this nifty little formula. If there are n trials in an experiment, an event has probability p of occurring in each of the trials, then the number of times we expect the event to occur is n times the probability. So the number of trials, 120, times the probability, 1/6, that gives us the expected outcome. Okay, that's a very simplistic example. We can talk about the expected outcome from one trial of an experiment or an event, a probability event. The expected outcome for the random variable x, which we have been talking about, is the mean result. It's the actual mean mu, but we're not going to calculate the mean like we normally do because we're dealing with probabilities. In general, the expectation of the random variable x is the expectation of x, e of x, equals the mean, equals the sum of the probabilities from, or I'm sorry, the sum of the trials times the probability. The formula that you are going to see on your formula sheet is this one. So mean equals the event times the probability of the event, or the number of trials times the probability of the event, and the sum of each individual one. Okay? Better explained in an example. It is a little confusing when you try and say it in words. So we will start off quite simple. Each time a footballer, thank you Australia, kicks for a goal, he has a 3/4 chance of being successful. In a particular game, he has 12 kicks for a goal. How many goals would you expect him to kick? Well, it's equal to the number of trials times the probability. So that's just simple. It's 12 times 3/4, and 12 times 3/4 is 9. Very simple. We would expect him to score or to kick 9 goals. Okay. Find the mean of the data of example 2. Well, that's the same as the expected outcome. So you have to be careful here. You're going to want to use your expected outcome formula because it's difficult to find the mean otherwise. And that was the magazine example, if you remember, from a couple of videos ago. And this is the table that I got. We had customers going to a store in 1 week, and the probability, they took the data. 23% of the customers purchased 1 magazine, 38% purchased 2, and so on. And they want to know what is the mean. And what we're going to end up finding here is the expectation based on 1 week's worth of data of the number of the average number of magazines that a randomly selected customer would purchase. Very simple. So all that means is that mu equals the sum of x times the probability that the event x is equal to x. What in the heck does that mean? All that means is we take the event 1 times its probability right here, 0.23, plus the event, each event, times its probability. That's all we do. So this is the event, and this is the probability of the event, and this stands for the sum for each of those. there isn't a number here. I guess you could put 5 because there's 5 here. They just don't want you to get confused with the numbers actually being the event. So let's see, 3 magazines would times 0.21 plus 4 magazines times 0.13 plus 5 magazines times 0.05. If you multiply that out, that comes to 2.39. So what does this mean? It means that in the long run, we can expect that the average number of magazines purchased per customer is 2.39. Okay, and that's based on 1 week's data. Not a big deal there. Okay, one more example, or one more concept, fair games. Fair games as related to gambling. In gambling, we say that the expected gain of the player from each game is the expected return or payout from the game, less the amount it costs them to play. The game will be fair if the expected gain is 0. That means the person running the game has the same chance as the exact same chance as the person playing the game, and that's if the expected gain is 0 over the long run. Now we know that's not the case for each individual event, that it's always going to be 0. It depends on the game. But if it's fair over the long run, we say the game is fair if the expected gain of the player is 0. So that is E of x equal to 0. So let's take a look here. In a game of chance, a player spins a square spinner labeled 1, 2, 3, or 4. The player wins the amount of money shown in the table alongside. So if they spin a 1, you win $1. 2, $2. Spin a 3, $5 you win. You spin a 4, you win $8. Okay. Determine the expected return, not the expected gain, the expected return for 1 spin of the spinner. So that is the return that a player could expect to get on 1 spin. Well, that's actually just the expected outcome, the expected return. So let's see. Let's say E of y, because we're going to use x for the expected gain here in a second. We'll let y be the return or payout from each individual spin. Okay, so you take the probability. If it's a fair spinner, the probability of spinning a 1 and each individual one of these is 1/4. So we would do 1/4 times 1, 1 for the $1 for the winnings, 1/4 times 2. If I spin a 2, I get $2, and I have a 25% or 1 in 4 chance of getting a 2, plus 1/4 times 5. That's the payout for a 3, plus 1/4 times 8, which is the payout for a 4, and that comes to $4. Okay, so the expected payout is $4. Okay, the expected gain of the player if it costs $5 to play each game. Okay, the expected gain is, well, if I pay $5, and my expectation of winning is $4, then the expected gain is negative $1. I'm expected to, on each individual one, the expectation would be that I'm going to lose $1. Now determine whether you would recommend playing this game. Well, no, because you're expected to lose $1. So the game is not fair. So we would say the expected gain, E of x, is not equal to 0. Okay, so therefore the game is not fair. Actually, the expected gain is equal to negative $1. So I would think we would advise someone not to play the game. Okay, that is it. We will see you next time.